So I'll be talking about integer programming and NP completeness today. So in class we touched briefly on the fact that integer programming is NP is a non-deterministic polynomial time problem, and this means that we basically have not found a polynomial time algorithm for integer programming. And it turns out that uh, there is this class of NP problems and P polynomial problems that we can separate problems into. Of course, there are problems that are outside of this range. For example, NP hard problems are um, non-determin non-determinist, or they're problems that are harder than non-deterministic polynomial time algorithms. And the thing I'll be discussing today is the fact that integer programming is a NP problem, but it is also NP complete, which basically means that um, all NP problems can be reduced to integer programming. Uh, Another example of a NP complete problem is Boolean satisfiability. Another also called 3CNF, which is a specific form of Boolean satisfiability. And the way I will show that integer programming is a NP complete problem is by reducing the Boolean satisfiability problem to integer programming. And the reason this implies that integer programming is a NP complete problem is because if we can reduce Boolean satisfiability to integer programming, and since Boolean satisfiability is NP complete, this means that every single NP problem can be reduced to Boolean satisfiability in polynomial time. And from there, the Boolean satisfiability problem itself can be reduced to integer programming. Then this whole thing means that any NP problem can be reduced in polynomial time to integer programming. And this is precisely the definition of NP complete. Um, and yep, and that's my reasoning behind it. And the actual reduction itself is quite easy, as shown in my blog post.